Greetings to all. In the last lecture, we have discussed the induction machine design with respect to the stator core, right. In this lecture also we will discuss and we will continue the design of stator core as well as rotor core. So, we have stopped at winding factor, right, where the winding factor equals to Kw is nothing but Kp into Kd. After substituting Kp and Kd in the voltage equation, then we can find the number of turns per phase. Once the number of turns per phase calculated, then we can select the what type of core or what type of coil with respect to the SWG data and what is the area of cross section and different copper weight and copper volume and resistance of the coil, all those things we will calculate it. Before going to that, we will discuss some example with respect to the winding factor Kw. Let us consider a 3 phase induction machine and 4 pole winding and 36 slots and short pitch winding, distributed type, distributed short pitch winding, and the short pitch is 1 slot. Find the winding factors for fundamental and third harmonic. Okay. First we will calculate the Q value, slots per pole per phase. Okay. Number of slots is equals to 36, poles 4, phases 3, Q equals to 3 slots per pole per phase. Then slots per pole is equals to 9. Okay. Coil pitch is equals to 9 means full pitch winding, right. Here one slot is short pitch is the given in the problem statement, that means coil pitch is equals to 8 slots. Okay. Then what is alpha? With respect to the one slot pitch, short pitch is nothing but, full pitch is nothing but 9 slots, equals to 180 degrees, that is one pole pitch, and 8 slots is the present coil pitch is equals to 180 into 8 divided by 9, right, it is equals to 160 degree. Now the coil pitch, the updated coil pitch for this winding type is 160 degrees. Okay. Here alpha is nothing but 180 minus 60, 160, then 20 degrees is the alpha. Now we will calculate the slot angle. Beta is equals to 360 by Qs into P by 2, 360 by 36 slots into number of poles is equals to 2 by 2, it will give 20 degrees is the beta value. Now we know the alpha value and we know the beta value. Substitute the alpha beta values in the winding factor equation. Okay. So, the winding factor for nth harmonic, for fundamental means n equals to 1, for nth harmonic means with respect to that particular harmonic we have to calculate it. First one is with respect to fundamental, right. For fundamental n equals to 1, that is kW1 cos n is 1, alpha is nothing but 20 by 2 into sin n is 1 for fundamental, q is nothing but 3, slots per pole per phase equals to 3, right. So, 3 into 20 degrees is the beta by 2 divided by beta q is nothing but 3 sin n is nothing but 1, 20 divided by 2. Okay. After calculating this thing, we will see kW1 is nothing but 9452. This is winding factor with respect to the fundamental. Similarly, winding factor with respect to the third harmonic, if we will calculate, cos n alpha by 2 means 3 into 20 degrees by 2 into sin 3 into q into beta by 2 divided by 3 is q into sin n beta by 2, n is nothing but 3, third harmonic, beta is 20 degrees by 2. So, this number if we will calculate, winding factor for third harmonic is 0.5774. So, now with respect to the fundamental, we can calculate the number of turns n phase by substituting the kW1 in the voltage equation. This is how we can calculate the winding factors. For example, another example I will consider, how to decide the short pitch angle to eliminate the fifth harmonic. I am considering one more example to eliminate the fifth harmonic. So, Kp is nothing but cos n alpha by 2, for fifth harmonic cos 5 alpha by 2. In order to eliminate fifth harmonic means Kp should be equals to 0, that means 5 alpha by 2 equals to pi by 2, alpha is equals to pi by 5. So, if we will make the short pitch angle pi by 5, then we can eliminate the fifth harmonic from the MMF wave. Okay. With respect to the induced EMF, fifth harmonic we can eliminate it. MMF is MMF with respect to the distributed winding, with respect to the short pitch winding only we can reduce the harmonics with respect to the induced EMF 1. Okay. Next we will discuss about the wire selection or SWG thing, how to select the SWG to make the winding. Next step, in order to select the SWG or in order to calculate the area of cross section, first we have to calculate the RMS current. What is I phase RMS current? We have to calculate the RMS current from the power equation, input power divided by M into V phase RMS into cos phi. This is equation number 5. So, from this equation power factor is known, V phase RMS is known, and number of phases also known variable, and P in also known variable. If we will consider efficiency equals to some number, let us say 90%, then P in we can calculate it, we know the P naught, right. Then P in is equals to P naught by efficiency. Okay. Once we know the I phase RMS, we can find the area of cross section with respect to the current density. Current density J is equals to I phase RMS by area of cross section of each conductor. Okay, this is equation number 6. Here current density is equals to, for copper we can select 3 to 5, 3 into 10 power 6 to 5 into 10 power 6 ampere per meter square, or we can say 3 to 5 ampere per meter mm square. Okay. So, depends upon the material, we have to select the current density and we know the I phase RMS and calculate the AC value, cross sectional area of each conductor. Then we can, based upon this area from the SWG data, we can find the which SWG is suitable for that particular current. Once we have selected the SWG from the data SWG data sheet, we have to calculate the copper area. Okay. This is the slot. Here n number of conductors are placed. Okay. So, copper area ACU is nothing but cross sectional area of each conductor into number of conductors per slot. Here number of conductors per slot is nothing but 2 into m into n phase by Qs, number of turns per phase into number of phases into each turn has 2 conductors, right, 2 divided by Qs. This is the total copper area with respect to a single slot. Okay. Now, we will calculate the length of a coil. We are going in detail with respect to the winding structure. So, copper area we have calculated and area of each conductor also we have calculated, and current rating, or we can say SWG data also we have calculated. Next thing is length of each coil. Okay. So, in order to find the length of each coil, we can see here the stator core. What we have to know is the length of the stator core. Okay. We can see here this is the stator core. We have to place the coils, right. We have done the how many number of slots required, what type of winding, and each coil consists of how many number of turns, and SWG data for each conductor also we have calculated. The remaining thing is how to calculate the length of coil and resistance of the coil and volume of the copper and weight of the copper. Okay. So, in order to calculate the resistance of a coil, we require first length of the coil. We can see here the coil is placed in the slots, 2 slots it is placed, and the length of each coil is nothing but 2 times the core length. Here we can see this is the core length. Okay. This one is the core length, and then some extra end winding also required, and then end ring length. Okay. We can see here I am drawing, these are the 2 conductors we are placing in the slots. Okay. We can see here these are the 2 conductors we are placing in the slots. Okay. And other thing is end winding. This is the end winding, this portion. This is the end winding portion on both sides. And in between there will be some straight conductor portion for making the proper winding arrangement or ending. We can see here this portion is nothing but end ring, circular based end ring, and this portion it is in a straight line with respect to the core. That portion is nothing but coil length with respect to the end ring, side, that is I am representing with x on all 4 sides, and this length is Le, that is core length including the air ducts and other things, and this is the end ring. Okay, this also end ring. This is length of one single ton, right. Like this n number of tons we are placing inside the slot. So, in order to calculate the length of a single ton, L single ton is equals to two times length of a core plus 4x is nothing but this portion where the coil came out of the core, but it is a straight portion. End ring will be this portion, the bended circular portion, but out of the core, the iron part, some straight conductor portion also there, that I am representing with x, okay, plus 2 times the end rings, end ring width. So, here 2 times Le we know, length of the core we know already, and 4 times x I am considering 30% of Le, 4x together I am considering 30% of the length of a core, plus end ring from this point to this point, if I will consider the semicircle, we know the radius, that is dis by 2, okay. Then we can find the perimeter, right, like 2 times the pole pitch is nothing but pi into dis by p, okay. This is the pole pitch or this semicircle radius or perimeter of this semicircle is nothing but pi d by p, into 2 will come because this side one semicircle and this side one semicircle or arc is there, that arc length is pi ds by p. So, this is length of a single coil, sorry, single ton. For example, each coil has n number of tons, n phase is the total number of tons per coil, okay, with respect to each and every phase. Per phase this many number of tons are there, then length of a total coil is nothing but n phase into length of single ton, that is equals to n phase into length of single ton is 2 times Le plus 30% of Le plus 2 times pi dis by p, okay. This is the total length of a coil per phase. Okay, length of a coil per phase is nothing but this one. Generally for small missions, this portion will be 22 to 40%, and for large missions where length of core is very high, during that time we have to consider 20 to 30%, okay, to make the extra portion of the straight conductor length outside the stator core, okay. If Le is small, we can consider that straight portion of the conductor to make the symmetrical winding 20 to 40%. This is the length of coil per phase with respect to the full pitch winding. Okay. Next we will discuss length of a coil with respect to the short pitch winding. The equation and everything will be same, okay, N phase 2 times length of the core plus to 30% of length of the core plus 2 into pi dis by p into some short pitch constant, that is alpha SC I am considering here, because once we will do the short pitch winding, the length of a coil or arc length will come down, right. Initially the arc length with respect to the full pitch winding, let us consider here 9 slots are there, okay. And then if we will reduce the distance between two conductors, let us say 7 slots, then the arc length also will come down, right, this portion. Here arc length is pi dis by p, that is pole pitch in mm. Here pi dis by p into how many number of slots we are short pitching, depends upon that we have to select the short pitch factor. Let us say if we are short pitching by an angle alpha, then pi minus alpha by pi is the short pitch factor. This one is nothing but short pitch factor. If let us say 1 slot we are short pitching or 30 degrees we are short pitching, then pi dis by p into pi minus 30 degrees means pi minus pi by 6 divided by pi, this is the nothing but 5 by 6 into pi dis by p. This we have to substitute here, alpha SC is nothing but 5 by 6, for example 1 slot is short pitched. So like that length of a coil is coming down, okay, for short pitch winding. This equation is for short pitch winding. So from this analysis, length of coil is coming down means resistance also will come down, then losses also will come down. Some advantages with respect to the short pitch winding we have discussed already. From this equation we can it will be clear with respect to the length, resistance is coming down and losses will come down and efficiency will be improved, okay. Once the length is calculated, next we have to calculate the resistance, phase resistance. Okay. R phase is equals to rho L coil per phase by area of cross section of each conductor. The resistivity of the copper will be 1.72 into 10 power minus 6 ohm meter. Similarly for different materials it will be different resistivity will be there. Here length we know and area of cross section of each conductor also we know, we can calculate the resistance per phase. Resistivity also known value, okay, only resistance is the unknown one. Next thing, once the resistance also done, what is the volume of copper? Okay, volume of copper with respect to each coil is nothing but area of copper coil into length of a coil, right. So we are calculating length of a coil with respect to each phase into conductor cross sectional area is nothing but volume of a coil per phase. For 3 phase machine, total volume of the copper is equals to 3 times area of conduction area of cross section with respect to each conductor into length of total phase coil, like length of a coil with respect to total phase. If we will do, then this is the volume equation, that is equation number 11, this is equation number 10 and this is equation number 9, equation number 8, equation number 7. Okay. I give the numbers to all equation. This is the volume of a copper. Then once we know the volume, we can find the weight of a copper winding. At the end we have to see the torque to weight ratio, power to weight ratio and everything, right. So first we have to see the what is weight of the copper winding, next weight of a core, stator core, then weight of the rotor core, iron material, and weight of the rotor winding, all those things we have to add, then that is the total weight of the complete machine. Okay. Now weight of the coil is equals to density of the material, copper material, into volume of the total copper winding. Okay. This is equation number 12. Here volume will be in a meter cube and density will be kg per meter cube. Then we will get weight in terms of kg. After calculating the weight of the copper with respect to the stator winding type, we have done the analysis. Next we can discuss the slot shapes, what kind of slot shape we have to select, and then slot geometry. So with this I am concluding this lecture. In this lecture we have calculated the how many number of turns required and what kind of pitch factors and distribution factors we have to select depends upon the winding type, and resistance of the each coil and length of the each coil and volume of the copper and weight of the copper we have discussed. Thank you.